Okay, it's time to start. Good afternoon, everyone. My name is Paolo Tonella. I will be the session chair for this exciting session on test quality and improvement. The first speaker is Shuai Wang, and he will be talking about test selection. So please come.
Thanks for the introduction. Hello, everyone. My name is Shuai from UIUC. Today, I'm going to present my work, Test Selection for Unified Regression Testing. Bug in code and misconfigurations are two main root causes of production failures in modern software systems. Large companies such as Google, Amazon, Microsoft got into big issues due to bugs and misconfigurations. Frequent software evolution makes it challenging to judge the correctness of software changes. Facebook actually got a severe outage in 2021 due to a configuration change that causing all Facebook services to a halt. Ensuring the correctness of changes for both configuration and code is important. Regression testing is one of testing technique for checking software code changes. When there are code changes, regression testing executes available tests to ensure that new code change did not break existing functionalities. It is widely used in modern CI/CD pipelines. However, most regression testing only tests code under the default configuration, but does not consider production configuration changes. Many code changes pass the regression tests under default configuration, but later lead to failures with production configurations. So configuration testing is then introduced to check production configuration changes together with code. The idea is to use C-test, a configuration test that is parameterized by a set of configuration parameters to check the production configuration and changes. Here is an example of a configuration test from HBase project. This C-test takes a configuration parameter that controlling max number of HTTP threads as input and checks the production config changes of this parameter under source code. However, existing configuration testing techniques assume that there is only configuration changes and the code never change. In modern software development, code and configurations are actually co-changing. Here are some Git histories of Hadoop common project that shows the configuration files is usually changed together with code files. Existing regression testing and configuration testing test code and configuration separately. This separation makes it hard to test the evolution of code and configuration. Also, it cannot catch defects due to the inconsistency of code and configuration code change. In this work, we present URT, Unified Regression Testing, to checking both code and configuration changes. Then we design a test selection algorithm to speed up URT with the same safety guarantee as previous tools. We implemented our tool on top of Ecstasy, a traditional RTS tool, and OpenCTest, a configuration testing framework. Finally, we evaluate the effectiveness of URT on 5 open source projects with hundreds of code revision and dozens of configuration files. Our evaluation is the largest RTS experiments performed on open source projects based on our knowledge. We released our data and code on GitHub. You can check it through the link below. So, URT stands for Unified Regression Testing. It generalizes traditional regression testing and configuration testing. It tests code changes under not only default configuration, but also the production configurations. Also, it tests configuration changes against the new code. Finally, in this unified way, URT is also be able to handle differences that has code and configuration code change. One problem with URT is that it may need to run each change multiple times under different configurations, since there are usually more than one deployed configuration in production. Existing regression testing is already very expensive, so URT will take even much longer time. It is necessary to have a way to reduce the URT time. Test selection is one technique to do the job. We propose URT as Unified Regression Test Selection to speed up the URT testing process. Like traditional RTS technique, the key idea is also to minimize the number of tests to run for a given difference. The table here shows the changes case and what tests need to be run in URT. For example, when there is only code change, URT runs regular test to check the code change, and it also runs configuration test to check the code change also works well under the production configuration. Our key insights to design URTs is that changes are typically very small for both code and configuration. Here we have three main observations. First, a difference changes a small piece of code or a small number of configuration values. Second, a production configuration changes only a small number of default configuration values. Third, the production configurations only differs in a small number of values. We designed the key selection strategy based on these three observations. I will describe it in the later slides. So basically, URT is built on top of traditional RTS techniques with three phases: analysis, execution, and collection. In traditional RTS, given a code and test, analysis phase first finds the code dependency and compares the dependency with the new code changes. If code change is related to the test, then it is selected to run and regenerate the code dependency based on the code changes. Otherwise, the execution will be skipped and the dependency keeps the same. URTs is very similar to traditional regression testing selection technique. There are change steps in each part. For input, URT not only consider code, but also consider configuration and its changes. Analysis phase find both code and configuration dependency for selection analysis. URT uses a two-dimensional comparison based on the key observations we mentioned in the previous slides for better selection performance. And the C-test runner is also added in the execution module. Finally, URTs collects both code and configuration dependency for further selection. Now let's take a look at URTs dependencies. So basically, dependencies are those entities that can affect test behaviors. URTs collects two dependencies, code dependency and configuration dependency. Code dependency is referred to the code that test accessed. For example, there are 4 tests T1 to T4 and 5 code files A to E. T1 accessed code file A, and A also depends on B and C. So T1 code dependency is T1 itself, A, B, and C. The same for others. Now, if code file C has changed, then T1, T2, T4 are related to this file change. Configuration dependency is on parameter level, so it records the configuration parameters used by the target test class. Similar to code dependency, if parameter P2 here has a value change, then T1, T2, and T3 are related to the change. Now with both code file C and parameter P2 change, all T1 to T4 are related to the change. With code and configuration dependencies, URTs performs two-dimensional comparison for C-test selection. The goal of this two-dimensional comparison is to select as few tests as possible while keeping safety. Given a configuration test, CT, parameterized by a set of configuration parameters P hat, now let's think of a situation with one default configuration and 2 production configurations. For any configuration setting, we have code dependencies and configuration dependencies. When there is new code and configuration changes introduced, URTs will first compare its dependency with the recalculated dependency under changes. This step is called vertical comparison. If there is no difference between the dependencies, it means that the new change is not related to the test at all. So vertical comparison will not select this test. Next, based on the observation we mentioned previously that configuration changes are usually very small and most of the configuration parameters may be the same even under different settings. So URTs also compares configuration dependency horizontally. In this case, C2 will compare its configuration dependencies with C1 and C default. Note that in this step, we do not need to compare the code dependency because horizontal comparison happens under the same code revision. Similar to vertical comparison, horizontal comparison will not select the test if there is no difference between the configuration dependencies. We can do this selection because as long as a test checks the same code and configuration, in terms of the same dependency here, it only needs to be executed once. The final decision is made based on the two comparison result. If either dimensional comparison has no difference, then this test is not selected to rerun. Our evaluation letter shows that two-dimensional comparison can reduce the number of tests selected by around twice compared with only one-dimensional comparison. We evaluate URTS on 5 large open-source projects with 250 code revisions and 100 configuration changes. We measure 2 metrics, end-to-end testing time and number of tests selected. We first ask how much can URTS save for URT. Our result shows that URT can reduce end-to-end testing time by 3.64 times and 1.87 times over retest all and safe ecstasy. Safe ecstasy is a safe RTS that considers all configuration changes. And the reduced number of tests by 8.92 times and 2.29 times over retest all and safe ecstasy. We also measure the overhead of introducing URT with URTS. The result shows that URT takes only 1.93 times on the end-to-end testing time over unsafe ecstasy, or RTS that ignores all configuration changes. Here is one example of comparing URTS with retest all and safe ecstasy within 50 code revisions and 20 configuration changes. The black point at the very top is retest all, and the blue shadow represents the difference between URT and safe ecstasy. We also measure the effectiveness of two-dimensional comparison and speed up for configuration-only changes. Due to the time constraint, I will not cover them in this talk. In summary, we represent URTS unified regression testing for checking both code and configuration changes. We design a test selection algorithm to speed up URT, and we evaluate the effectiveness of URTS on 5 open source projects. We release our data and code on GitHub. You can check it through the link below and try it with your projects. Thank you.
Thank you. How do you match a configuration to the test? Is it just like coverage, or do you really check if the assertion actually checks the correctness of the configuration?
Yeah, thank you for the question. So the projects we're measuring usually have a unified configuration API, and our tool instrument those API to dynamically tracking which parameter is actually used by which test, so that we can get the configuration parameter dependency on the parameter level. Yeah.
Hi, thank you for your talk. So in your example for the code dependencies, I saw that there is you also considered indirect dependencies as well, like those code that were covered indirectly, not directly. So did you consider comparing the approaches? Yeah, if you only consider direct dependencies versus indirect dependencies?
We're built on top of a test selection tool called Ecstasy, and we directly use their techniques. So we haven't measured this indirect approach, but I would agree this could be probably select less tests, but the safety would become an issue if you do not consider the indirect dependency.
Thank you.
Okay, no questions? No, let's thank the speaker again.
Thank you.
So, hello everyone, I'm Rongqi from the University of Ottawa. Today I'm going to present my work, ATM, Black Box Test Case Minimization based on test code similarity and evolutionary research. So let me first introduce test case minimization. So the problem is that there will be many redundant test cases in the test suite, and those test cases are unlikely to detect different faults. So if we run all of them, it will be a waste of time and resources. So the solution to this problem is test case minimization by permanently removing the redundant test cases in the test suite. So based on the literature we reviewed, the existing test case minimization techniques can be classified into white box techniques and also the black box techniques. So most of the test case minimization techniques are relying on the production code. However, the production code is not always accessible by the test engineers. And also like the code coverage features and also the coverage analysis is usually really computationally expensive. And the other category of the test case minimization techniques are black box techniques. So the most current state-of-the-art black box technique is called FastR. So they only rely on the test code only, and it is much more scalable than the white box techniques. So based on all the literature we reviewed, we proposed our approach ATM, which is an abstract syntax tree-based test case minimizer. So our motivation is to achieve a better trade-off between effectiveness and efficiency than the FastR. So these are the main steps of our approach. So first we have a test suite, then we pre-process the test code, and then we transform the test code into ASTs. And based on these ASTs, we use 4 different tree-based similarity measures to calculate the similarity between all pairs of test cases. Then we apply the search algorithm, like the genetic algorithm and multi-objective search NSGA2 to using those similarity measures to minimize the test suite. And then, so this is the first step of our approach, which is test code preprocessing. So we basically remove all the information that is irrelevant to the testing logic, such as the test case names, and also the comments, and also login printing statements, and also we remove the assertions. And also because that similar and identical test cases may have different variable identifiers. So we also normalize the variable identifiers. So the next step is to transform the preprocessed test code on the left-hand side to the corresponding abstract syntax tree. And based on the ASTs, we used 4 different tree-based similarities. For example, we used the top-down similarity, which more like capture the structure-oriented information, and we also used the bottom-up similarity, which is more like to capture the detail-oriented information. And also, we created our own new tree-based similarity, which is called combined similarity, by taking the union of top-down and bottom-up similarity. And finally, we also used the tree added distance, which captured the scattered code differences. So after getting all these similarity values, we applied the genetic algorithm. So we first initialized the population by randomly selecting a subset of test cases, and we evaluate the subset using the similarity value as fitness. After that, we do the selection, crossover, mutation, and this process iterates until it reaches the termination criteria. And finally, we have the minimized test suite, which contains the diverse test cases. So we use both a single objective genetic algorithm with each of the similarity measure as fitness, and also we use the multi-objective search like the NSGA2 combining 2 of the tree-based similarity measures as fitness. As for the evaluation of ATM, the dataset we used is 14 Java project with 661 versions extracted from the defects4j dataset. And each version has a single real fault that is related to the production code. And as for the baselines, we consider random minimization, and also, as I mentioned before, the FASTAR, which is a black box test case minimization technique, and which is also much more scalable, efficient than the white box techniques. And but however, this technique achieves a relatively low fault detection rate for the Java projects. So finally, as for the evaluation metrics, we measure the effectiveness using the fault detection rate, and also we measure the execution time for evaluate the efficiency of our approach. And we also perform our experiments using 3 different minimization budgets. So this is the results of all the configurations of our approach under 50 minimization budget. So the time is in minutes. So we can see that the highest fault detection rate is achieved by using the NSGA2 with the combined and tree-added distance similarity, which is 82%. And also, we can see that our approach runs within 1 to 4 hours on average per project version. And also, we choose the best configuration of our approach is the GA with combined similarity, because when we consider both the effectiveness, because it achieved 80% in terms of fault detection rate, and also as for the efficiency, it ran like 1.2 hours per project version. And this is the results of comparison with FASTAR and random minimization under 15 minimization budget. The time is in seconds. So basically, ATM achieved significantly higher fault detection rate than FASTAR, which is like almost 20% higher in terms of fault detection rate on average. And also, it achieves much better than the random minimization, which is like almost 30% in terms of fault detection rate on average. And as for the execution time, we can see that because the time is in seconds, so it's very the 8-hour approach run like longer than the baseline techniques. However, because the test case minimization only occasionally applied, because it only applied when many new test cases are added to the test suite. So we consider our approach run within practically acceptable time, and also the results are consistent with other minimization budgets. So finally, to summarize that, our approach performs significantly better than the baseline techniques without requiring production code analyze. So it's also much more scalable than the white box techniques. And also our approach achieved significantly higher fault detection rates than the baseline approaches with practically acceptable time. And however, our approach has a scalability issue because on the largest project in our dataset, which is the name of the project is time, which has nearly 4,000 test cases, our approach took like more than 10 hours for both like the similarity calculation and also the minimization process on average per project version. However, this scalability issue can be easily mitigated by parallelizing the calculation of the fitness, and also we can somehow improve the way that we calculate the fitness. So that's for my work. Thank you for listening.
Hello, hi. Yeah, sorry. I have a question about the evaluation. I was a bit confused. You said that you do minimization for each version and then evaluate whether you can detect a bug on that version.
So you are asking about the way that we calculate fault detection rate?
Well, even the minimization, do you do it for each and every version separately, or do you do it only once?
We do it once for each version of each project.
Okay, but what would that correspond to in practice? I mean, I don't understand. Why would I minimize for each and every version of my code?
So for each code releases, we have the test suite, right? So we minimize the test suite for that code release.
But then you evaluate on the future releases whether it finds bug, or you evaluate on that same one whether it finds a bug?
No, not the same one. In the future, we have new test suite, and if there are many new test cases added to the test suite, so we can perform the test case minimization again.
Oh, okay. Maybe we can take it offline. I still don't understand. Okay.
Okay.
So I had a question about, it feels like both the white box and the black box approach are sort of kind of like a static detection of these issues. And I was wondering if you had investigated, like we have CI systems. You very well, for a large project, may have logs of all of the past failure rates for every pull request for a while. Do we look at, historically, these things are generating the same signal?
So you mean that we can use the execution history information?
Right, because CI logs and those sorts of things.
Yes, actually, I saw many literature using the execution history features for minimization. However, we think that in practice, those information are not always accessible by the test engineers. So sometimes it cannot be adapt to like other projects.
I'm not sure I believe that statement. Like I think that 20 years ago it was much more common for there to be a air gap between test engineering and development. I have not heard of any groups that are still holding to that, so I would question that assumption a little bit.
So let me make sure. So you are not sure that the execution history are not accessible by the test engineers?
I'm not sure that there's a difference between test engineers and engineers in many domains, and there's certainly not like you don't get to see the code, you don't get to see the test results.
But actually, in practice, for example, sometimes we work with the industry. Usually, the industry doesn't provide the production code. So that's our experience. So
Okay.
that's why we do it.
Yes, that I can believe.
Yes, but it's really good
yes.
to know that, actually. For example, if I know that we can have the production code and the history, we can have many new ways to adapt to many new projects. Maybe we can have better results.
Yeah, speaking as an industry rep, like the whole approach or the whole problem space of there are so many tests. Could we please do better selection, prioritization, reduction, like removal of duplicates? Like this does seem like a valid problem space. Yeah.
Thank you for your question.
Hello, thanks for this presentation. Just in the preparation phase, a quick question. You prepared the test case, you cleaned up common word and so on. So why did you do this? Because you wanted to process faster, or because the technique worked better? Because in FAST there is no cleaning. The tests are taken as they are in all the FAST family.
Oh, okay. Thank you for your question. Because so you mean that why we do pre-processing, right? So actually, because we consider that there are many irrelevant information from the test code, and that might affect the similarity of the test cases. So that's why we do the pre-processing. But it's a good question because actually we think that maybe some information in the test code is also relevant to the similarity, right? Yes, I also agree. So in the future, we will investigate that we do not remove any information. Maybe we can get a better result. But thank you for your question.
Okay, let's thank the speaker. called gaps in structural testing. And the speaker is Soneya, please.
Good afternoon, everybody. My name is Soneya Binta Hossain, and I'm presenting our paper on measuring and mitigating gaps in structural testing. This work was done in collaboration with Professor Matt Dwyer, who is my advisor, Professor Sebastian Elbaum, and research scientist Anne Nguyen. We all are from Les Lab at the University of Virginia. We all are familiar with code coverage, which is extremely popular and widely used test adequacy metric that measures the percentage of code base that is executed by a test suite during a testing process. In our paper, we have investigated 13 large-scale Java applications. Let's take a look at the code coverage of 2 out of those 13. The first artifact is Apache Common CSV, which is a Java utility package that allows for easy reading and writing of the CSV files. And this test suite achieves a code coverage of 98%, which is extremely high code coverage. And it indicates that the package is very well tested. The second artifact is Jackson Data Format XML, which is also another utility package for Java. And the test suite achieves a code coverage of 61%. This low code coverage indicates that this package is poorly tested. Now, based on the statement coverage, it seems that CSV is way better tested than Data Format XML. However, the question is, would we be able to say the same thing if we also consider the quality of test oracles in addition to code coverage? Feel free to read our paper to find that answer, and I can also share the answer as I progress through the presentation. But before that, let's take a brief tour through the literature to explore why prioritizing the quality of test oracles is crucial even when code coverage information is easily obtainable. The main goal of software testing is to detect bugs. Numerous studies have investigated how code coverage relates to fault findings. And almost all of the studies agreed that although code coverage is crucial, it doesn't provide a full picture of the quality of the test suite in terms of fault detection effectiveness. On the other hand, research on test oracles and fault detection effectiveness showed that test oracles play a critical role in software testing, and there is a strong correlation between test oracles and the fault detection effectiveness. Therefore, to overcome the limitation of traditional code coverage and to incorporate test oracles, researchers proposed structural code coverage based on test oracles. Checked coverage and state coverage are noteworthy. Previous oracle-based metrics support mostly statement coverage criterion and are only used for the sole purpose of assessing the test suite. Our research is built on checked coverage proposed by David Schuler and Anders Geller, and we showed that it is possible to extend this notion of oracle-based coverage for stronger coverage criterion. Those are highly recommended for testing safety-critical systems. And we introduce and study the concept of coverage gap, and we explored this coverage gap as an opportunity to further improve the test suite's quality to achieve better fault detection effectiveness. Therefore, the focus of our paper is to measure gaps between code that is executed and code that is checked by test oracles. We refer them as coverage gap. And we also explore the impact of coverage gap on fault detection effectiveness. And then lastly, we mitigate the gap by enhancing the test suite so that we can achieve better fault detection effectiveness. Now let's take a quick look at one of the simple examples. This is a Java code that defines a triangle class. It has 5 instance variables, 3 sides, 1 perimeter, and 1 color variable. In total, it has 8 statements, and this is a simple test case that can achieve 100% code coverage because it executes all the statements. And taking a closer look at the test oracle, we can see that there is only one oracle that checks the get color method, and this method depends on statement 8 and statement 4. So 2 statements are executed and checked by test oracle. Rest of the 6 statements, they are only executed but not checked by any assertions. Therefore, we call them in the gap statement. So in summary, this code achieves 100% code coverage, 25% checked coverage, and 75% gap. Now, we take this gap information as an opportunity so that we can improve the quality of the test suite. all the statements marked with red colors are in coverage gap. To do that, to mitigate this gap, we propose a recommender which is implemented on top of ASM bytecode manipulation library. Therefore, it's extremely lightweight, and it supports interprocedural flow-sensitive static analysis of the gaps and the system under test. The recommender recommends a set of focus methods that should be included in the test suite and whose results should be checked using test assertions. The recommender mostly analyzes the read-write relationships among the unchecked statement, and it comes up with some recommendation. Here, analyzing the unchecked statement, the recommender successfully suggested that we should call the getPerimeter method in the test case, and its results should be checked using test oracle. Once we add this test oracle, it can achieve 100% checked coverage and 0% gap. So this is a very simple example, and looking at this example, one may ask that why we need this recommender system, but in practice, the programs are larger scale, has hundreds and thousands of statements, so it is very difficult to come up with this recommendation manually. And we apply this technique to 13 larger scale Java applications consisting of 16,000 test cases and 52,000 test assertions. We answer 4 research questions. In the first research question, we investigate the gap in the developer written test suites for 13 Java applications that I just mentioned. And in research question 2, we analyze the impact of gaps on fault detection. In research question 3 and 4, we investigate the performance of the recommender, and we analyze how the recommended assertion improved the fault detection effectiveness. Because of the time constraint, I am only going to discuss in detail research question 2 and 3. But in research question 1, we found that on average there is a 35 percentage point gaps in the investigated artifacts, meaning that 35% of the statements are only executed, but they do not influence any of the test oracles. And in research question 4, we see that using our recommended assertion, we can achieve way better fault detection effectiveness, such as much as 57 percentage point and on average 13 percentage point in the class level. Let's move on to research question 2, where we studied the impact of coverage gap on fault detection effectiveness. To do that, we systematically manipulate the test suite to vary the coverage gap, and we generated 180 test suites. We used mutation testing, which injected 96,000 mutants, and then we performed the mutation study and find the correlation between the gaps and the kill score. In the paper, you will find this experiment performed in different granularities, such as application and package level. We also use statement criterion and object branch criterion, but here I have only presenting four plots. This x-axis shows the statement coverage gap, and the y-axis shows the kill score. The correlation coefficient is more than 90% for all of the plot, and there is a strong negative correlation. This indicates that the more the gap from the test suite, the less the fault detection effectiveness. And the less the gap, the better the fault detection effectiveness, which actually means that a developer should always aim to reduce this coverage gap so that it can achieve maximum fault detection effectiveness. Yeah, so in summary, fault can hide in the coverage gap, and there is a strong negative and statistically significant correlation between gap size and the fault detection effectiveness. In research question 3, we investigated the performance of the recommender. To do that, we removed the developer written assertions from the test suite, and then we compute the resulting gaps, and we analyzed the system under test and the gap to recommend focus methods. And then we compared the recommended focus method to the focus methods that were in the removed assertions. Similar to RQ2, we applied this research question to all 13 artifacts, and we have seen that our recommender is able to recommend almost for 46% of the removed assertion, it can recommend the focus method within top 1 recommendation. And for 67% of the removed assertion, it can recommend the focus method within top 5 recommendation. And when go to top 10 recommendation, we see that it covers almost 73% of the removed assertions. Also, please note that it is possible to cover unchecked statement many different ways. So all the candidate focus methods are correct, but it just, we only checked one-to-one mapping to the removed assertions to the recommended assertions. So in summary, for 67% of the focus methods, the original test suites original suite is suggested within the top 5 recommendation, and when we restrict to the top 1 recommendation, nearly half of the developer written focus methods are suggested by the recommender. In summary, we could say that traditional code coverage can be very misleading, which was also suggested by many other previous research, and gaps can better reflect the under-tested program components. In this paper, I haven't studied the cost component of the computation. However, I noticed that computing dynamic program dependencies is costly and time-consuming. So moving forward, scale forms of this assertion-based coverage are highly expected, and where we can leverage this gap information to further and automatically improve the test suite effectiveness. And thanks, our artifact is available in GitHub, which is reusable too, and we thank DARPA, ARCOS project, and Air Force Office of Scientific Research and Lockheed Martin Research Laboratory for funding our research effort. Thanks for your attention.
Thank you for this very important look at beyond structural coverage. Now, from your example, I was wondering if you're dependent on the tests that are already existing, right? So you were showing the bug, and depending on which numbers the object is initialized in, you might not even be able to expose the fault. So is there still, like, are you already changing the input parameters of the test cases, or should we still work on doing that as well?
So here, you talked about the bug, right? Yeah. In line number 3? Yeah. So the bug is there, and the bug is executed, but the Oracle is not able to catch it because this statement is not influencing any of the existing test oracles.
Exactly, and then in the next one, you add an oracle, but let's say the triangle would be initialized if you have the same for A2 and A3, just get the same value.
No, it would be 8.
Let's say it would be.
Right.
Then you wouldn't be able to find this. So I wonder, do you also vary the input phase of the test case?
No, so currently the scope of this research is to bring the statement to the influence of under the influence of test assertion, so that, and the thing you are talking about is oracle problem. So I mean, it depends on different type of inputs, whether the fault is depending on certain area of the inputs. But no, we are not handling that. Currently, this research is only making sure that the executed statements or other kind of criterion, such as branch or object branch, they are actually influencing the test oracles. Yeah, hopefully that answers the question.
So, potentially related question.
Who is asking?
Me. Hi. Back here.
Oh, hi. Yeah.
Hello. Potentially related question. So something that we observe in software testing frequently is that defects are triggered not by a single statement, but a combination of statements, or maybe occurs in some form of second-order logic, right? How does your particular strategy perform when the oracle may have a data dependency on a line which is present, but there is, or which is present in the data dependency graph, but perhaps is not triggering the defect?
Sure, that is possible. I'm not. So let me confirm. So if some statements or other component is in the dependence chain and there is a defect, then the only thing that could affect not the fault to be discovered is weaker assertions or weak oracles. So that's again an oracle problem, but if the assertion is strong enough and the defect is in the dependence chain that is flowing to the test oracle, then I think the defect should be exposed or covered.
Right. My point is more along the lines of one of the central claims is that the coverage is a misleading metric, but while it is an improved metric, is the metric of whether or not the data dependency graph impacts the assertion, right, also misleading? Because you still have this problem of, yes, your oracle does test that it's dependent on a particular point of coverage, but that doesn't actually indicate whether or not that particular line has been well tested. It just says whether or not it could be tested. Yes?
Sure. This is definitely a necessary condition for a fault to be exposed, but then there are other factors that is also necessary, such as your oracle needs to be strong, like I mentioned. So the first necessary condition is that your statement should be executed first, and then it should flow to some of the test oracle that is checking the component, and then comes to the strength of the oracle. So there are different levels. So we are top of the statement coverage level, but then there should be some other metric that could actually measure the strength of the oracle. There could be very weak assertions. Those are not, so hopefully that answers the question.
Unfortunately, we have to stop the question answering.
I could answer your question when I come back.
There's
Thanks.
a lot of other questions, so you can take them offline.
Yeah. Thank you so much.
Okay, so let's thank the speaker again. And the next presentation is a demo presentation given by Martin Gruber, and we will be listening about mining flaky Python tests. Please.
Hi, everyone. My name is Martin, and today I have the pleasure to present to you our work on mining flaky tests. So, a flaky test, as you might know, is a test that can pass and fail on the same version of the source code. And this is an annoyance to developers because they have to deal with test failures that had nothing to do with the changes that they make in a continuous integration regression testing setup. And about 10 years ago, researchers became interested in this phenomenon, and they started studying it and proposing mitigations and ways to detect and fix and debug flaky tests. And in order to do all of those things, they need, they need some study subjects. So whenever you develop a treatment, you need some guinea pigs to try it out on, right? So this is where FlaPy comes into play. So if you're researching on flaky tests, we can provide you some guinea pigs to try out your method on. And so what is FlaPy? FlaPy is a tool for automatically rerunning test suites of Python projects. So what it basically does is you provide it with a set of GitHub URLs that include Python projects, and it's going to automatically check out the desired version. It's going to try to install dependencies from the repository and executes the test suites contained in those projects in an isolated manner that can be parallelized across a Slurm cluster. And finally, you can use FlaPy to collect all the results and get a nice and concise table of all the tests that have been executed and how often they passed and failed and whether you found some flaky tests. So let's have a look at how to use FlaPy. So you start with cloning it from GitHub, and you can directly jump into the entry point, which is called flappy.sh. The only system dependency that you have is Docker. And from there, it tells you that it offers multiple subcommands, which is running, first of all, sampling tests from PyPI, which is a Python package index, running those tests, or parsing the results. So let's go ahead and run some test suites. What you have to provide here is an input CSV file where for each row you have specified the URL or the local path that you want to clone or copy from. And in orange, where we can see at the very back here, you have to provide the number of times you want to execute the test suite of the specified projects. And what you're going to get out of that is this output directory structure, where at the very core you can see these output.xml files. So these are JUnit XML files which report how often, also which tests have been executed and whether they passed or failed. However, you do not have to look at any of this very nested, difficult structure. So instead, you just take your output directory and feed it back into FlaPy, into the parse command, and tell it to give you a test overview, which looks something like that. So for each row here, represents one test case that has been executed, and in the columns you can see how often it produced what kind of verdict under which kind of configuration. So how often it passed and failed when run in same and in random order. So FlaPy also offers the opportunity to shuffle your test cases in order to detect order dependencies. And based on that, it can also judge what kind of, if the test is flaky, and what kind of flakiness you're dealing with. So for example here, these tests are non-order dependent flaky because they manage to pass and fail when run in the default order. However, the one at the bottom here is order dependent flaky because it behaves the same way when run in same order. However, if you shuffle the test order, it actually managed to both pass and fail. So we have created a tool called FlaPy, which should help researchers who work on test flakiness in order to get some guinea pigs for their experiments. The core features of FlaPy is that you just give it a set of GitHub URLs, it checks out the code, it executes the test suites in there, and it gives you a nice interface to pass back the results. Yeah, as mentioned, the only thing you have to provide is the URLs and the number of times you want to execute the test suites. And it gives you a nice table with all the tests that have been executed. Thank you very much.
Do you have an example of the when you shuffle the order, the test becomes flaky?
Yeah.
That seems surprising to me.
Yeah.
That seems like a bad test or a brittle test, but I'm not sure about it being random.
Yeah, very good point. So order dependency is a special kind of flakiness, which basically says if you run it in random order, it will sometimes pass and sometimes fail. But if you run it in the same shuffled, in the same order, it will either pass or fail. So I think what you're referring to is that I can just run it in the same order and it will produce the same result, right? So why is that flaky? And the answer to that is order dependencies are bad because if you add, that's kind of the answer. Because if you edit your test suite, if you delete tests, if you run them in parallel, this is all very much affected by order dependency. And so it's a special kind of flakiness, and you can argue about it if it should be in the same category as the others. Yeah.
I have a comment, not a question. Just like to say that the artifact was great. I've had undergrads who were able to use FlaPy and get good results. So anything that works with undergrads is already great. So for those who are interested, try this tool out. It works for reals.
Thank you so much. Thank you.
So I think we have to switch to the next speaker.
I had a question.
Yeah, maybe you can take it offline because we are out of time. Sorry. The next speaker is Amrad Riza, and he will be talking about test case prioritization.
Okay, hello everyone. My name is Ahmad Reza, and I'm from University of Ottawa. Today I'm going to present to you my work about test case prioritization, specifically scalable and accurate test case prioritization. So we know that regression testing is like time-consuming and resource-extensive in large-scale continuous integration environments. One solution to this problem is detecting the faults earlier and faster to notify the developer by using machine learning-based test case prioritization, or ML-based TCP. For example, if you run the test cases in a normal order, for example, here you need to wait about 35 minutes to detect to be notified about the first fault. However, if you have a good TCP solution, you can just get notified in the first 5 minutes. Our contributions is that first we define a comprehensive feature set from all the CI data sources for finding machine learning-based TCP solutions. We provide a benchmark of 25 subjects, and they're carefully selected. And we answer 4 research questions to identify efficient and effective TCP solutions. The test case feature groups we include or we study is 3 feature groups. The first is the test code itself, which includes the development process of the test code, the complexity of the test code, and also the changes as made to the test code. The second feature group is about the execution records. It basically includes the verdict and the duration. And the third group is related to the covered code. It includes the coverage metrics and also the same code metrics that we used for the test code. But here is for the covered code. In the first research question in our work, we investigated the data collection time of these feature groups. And the first finding was that feature groups vary in data collection time, and more specifically, the covered code is the most expensive, and then it comes the test code, and then the least expensive is the execution record. The second finding is that subjects also have an impact. More specifically, the project size and the test suite size, if it increases, the data collection time of all features are affected, and they also increase. The takeaway is that machine learning-based TCP is affected by the feature used and also the size of the project and the size of the test suite. In the second research question, we investigated the contribution of the features or the feature groups to the effectiveness of the TCP. And we found that if you train the machine learning models on all features, you get the best results. In the second place, if the machine learning models are trained only on the execution records, or the machine learning model is trained only on the test code, you get the second place of the results in terms of effectiveness. And then in the third place, we have the machine learning model that is only trained on the covered code features. In this research question, we also investigate the most important features, which are the complexity and the development process of the test code, and also the duration of the test code. These were among the most important features in our machine learning algorithm. In the third research question, we investigated the retraining suggestions. Do we need to retrain our machine learning models and collect the data on every CI build or not? We found that if you're targeting the best TCP effectiveness, you need to retrain the model on every build. However, if you want to save some time and resources, you can train at most every 10 builds on average based on our subjects with a small TCP effectiveness loss. And finally, in the fourth research question, we investigated the trade-off between the cost and effectiveness as a summary, as a wrap-up. And we found that, again, if you train your machine learning models on all features, you have to spend the highest cost. However, you get the highest TCP effectiveness. On the other side, if you train, we suggest that training the machine learning model only on the execution record features gets the lowest cost. You need to spend the lowest cost, but there is a small decrease in the effectiveness. To summarize the work, we studied 3 feature groups in TCP. One is the execution record features, second is the test code features, and third is the covered code. And we identified effective and efficient TCP solutions. Our key findings were that covered code are the most expensive to collect, yet the least effective. The execution record features are the least expensive, and they have acceptable TCP size results and effectiveness. And also, retraining less frequently saves some resources for you. However, it causes small effectiveness loss. Thank you for your attention.
Thank you. You showed that after the history, the test code features are actually very important. Like, I know this is not causality, but does it mean that the tests are more failing because of the tests themselves than because of the code that they are actually testing?
This is actually because of the history. So the test, basically the development process is related to the history. The duration is related to the history. The complexity is is like the complexity metrics that we used are the number, like for example, the number of lines, the simplest metric, the complexity metric. So if there, for example, the test case is bigger, it's like we can infer from that that is actually executing a more complex code. So there's a relation between the complexity of the test code and the code it tests. It's not just isolated test code.
And it might also be just influenced by the history because it was failing more in the past. They have more changes, they have more complexity in those test cases.
Yes.
That might be connected as well.
Yes, especially the development process, yes.
Mm-hmm.
Thank the speaker again. And the next speaker is Sakina Fatima, and she will be talking again about Flaky tests.
Hello everyone, I am Sakina from University of Ottawa, Canada. And I will be presenting my work, FlaPy, a black box language model-based predictor for Flaky tests. So, Flaky tests are those tests that fail and pass for the same version of the code under test. That is, they show an indeterministic behavior. These tests are hard to reproduce as these tests have to be re-executed several times, which is computationally very expensive, especially in large-scale systems. Google and Microsoft have reported several test failures, which were as a result of test flakiness. These tests hide the real bugs in the system which they are supposed to test. And then the tests become unreliable because no one knows that at what number of execution these tests will fail. Lastly, it delays the software release process in general. So before I explain our objectives, the traditional machine learning classifiers have been used to detect these flaky tests in order to avoid their rerunning. But these techniques require predefined features to train these classifiers. And further, these techniques are not black box, which require access to the production code or the coverage information, which is expensive to collect, especially for the large-scale systems. And lastly, these techniques are not generic or specific to programming language and projects. So we aim to develop a technique which is black box, that is, it only relies on the test code, and it requires no definition of features as in other traditional machine learning classifiers. And it is generic, that it can be used for different programming languages and for different projects as well. So what we want to do is that we have a test case, we pass it to the model, and the model, just based on the test case code, detects that this test case is flaky or not flaky. So to do that, we have used the pre-trained programming language model, CodeBird, that has been pre-trained on different programming languages. We have fine-tuned it with different very popular data sets of flaky tests independently using a feed-forward neural network. So our solution, actually FlaPy, answers following two research questions. The first one is how accurately this language model-based predictor, FlaPy, is able to predict flaky test. And to do that, we evaluated our technique on two different data sets of flaky test using two different validation techniques, that is cross-validation and per project validation. Secondly, we compared the performance of our FlaPy with state-of-the-art machine learning-based classifiers of flaky tests to see how we perform better than these traditional classifiers. So as you can see in the results, FlaPy outperformed significantly the traditional white box and black box machine learning classifiers of flaky tests on both two data sets and for both validation techniques as well, like cross-validation and per project. However, as we all might be familiar with that these language models have some limitations. So CodeBird has this limitation that it can only take up to 510 tokens per code input. So if the test cases are long, some of their information will be truncated because the CodeBird will not be able to process that. So to help with that, we pre-process the test cases in a way that we only retain code statements in the test case that are relevant to test smells, because test smells have a high relationship with test flakiness. To do that, it's just an example that we have a test case here, and it has these statements that are related to different types of test smells. We pre-process the code in a way that we only retain these statements related to test smells in this test case. So this leads to our research question number 3, that how does pre-processing improve the performance of our technique? So we see a significant improvement in our results based on this pre-processing on both data sets. Summarizing our contributions is that we developed a generic black box language model-based predictor for flaky tests that does not require any rerunning. We significantly increased the performance of the prediction results for the flaky test as compared to existing ML-based solution. We significantly improved our own results by the code preprocessing based on test smells. And lastly, we reduced the cost for debugging test cases and debugging production code by 10 and 18 percentage points, respectively. So that's it. Thank you very much.
Hi, thank you for your presentation. Could you shed some more light on your data set in general? So you said you wanted to build a model that was programming language agnostic. So could you, what kind of programming languages were there in your training data set, and what was the performance of the model for those languages?
Okay, so if you just want to know that what was the structure or what was the type of the data set that we used to fine-tune our model, right?
What the examples that you had in your training, right? So let's say you had Python, JavaScript, Java.
Okay.
Right.
So the first data set that we used, it's a very popular data set of flaky tests, and it has the maximum number of tests as well. It's a Java-based data set, and it's from the Flagger. They reran the test cases 10,000 times, each test case 10,000 times to determine that whether a test case is flaky or not, so that we use that as ground truth labels to do our classification, the first one. The second one is also like a Java-based data set of flaky test. It's called International Data Set of Flaky Tests, but it's a small data set. We only consider 455 tests from that because we were only looking for those test cases where the flakiness relies in the test code, because we are not accessing production code for this work.
So you're only focused on Java then, right?
Yes, for this work, yes, because yeah.
Language agnostic is a future version.
Okay, any more questions? There's one on the back. And I'm afraid it will be the last one. We have to switch them. So, one of the two.
Okay, thank you. Give me the opportunity to ask a question. Actually, that's great. Actually, your approach, you don't need to run the test from repetitively. Probably developer will really like it. But the things actually, developer hate the flaky test. That's annoying. But when you detect the flaky test, then report flaky test to them without very strong evidence, then they may respond differently. Say you tell the developer, oh, this is a flake test, but without kind of evidence, just say it's a flake test. Probably they don't think so. There's a flake test. You don't have enough evidence say there's a flake test. Then how do you comment on these cases? Even you detect a lot of flaky tests, then you report to developers, but they don't buy it if you don't have the strong evidence. Because I'm not sure your approach is based on machine learning based. Do you have some kind of other output, say, this is a flake test, you have some evidence or clear rule or cause test smell to show them that actually exactly flake test, probably you can spend some effort, investigate it. Can you comment on that?
Yeah, thank you very much. I think at the moment for this work, we just based on our training data set, and we believe that the ground truth that we have to train the model is correct. So based on that, we then predict or classify the flaky tests, and as you can see that the prediction results were very high, so we assume that our model is working correctly and if it says that a flaky test is flaky, it is it has high chances to be flaky. But at the moment, we don't pinpoint that what is causing flakiness in a test code that we have mentioned, we have classified as flaky. So yeah, for the future work, we can look into that as well, that our model can also pinpoint the line number or the cause, which is the root cause for the flakiness in that test code. Thank you.
Okay, let's thank the speaker again. The next speaker is Caroline Brandt, and she will be talking about test amplification.
Hello, everyone. I'm Caroline, and I'm going to tell you about our project with Andy together on how we try to make test amplification a more developer-centric process. And we've heard testing is super important, and we all know that, but software developers also find it a lot of work, and they find it tedious to test their own code. And one way that research is trying to address this is by giving them automated tools that can generate these test cases for them. And we have really powerful tools out there that can give us super high coverage for our code. But the problem is that the developers are still not using them in their day-to-day development to help them in this testing effort. And our hypothesis is that one of the reasons for this is that we don't think enough about how the developers and the tools are actually going to communicate with each other. And that's what I'm investigating in my PhD research, is how to design this interaction between developers and test generation tools. The technique that I'm applying is test amplification. So this is how we generate the test cases. And here we already have some test cases that were previously written by the developers of the project. And we take them to generate the new test cases. We mutate the input, we change the values to the parameters, or we call some new methods. Then we replace the assertions with new values because we have some new behavior that we now need to assert. And in the end, we measure, do we somehow improve our existing test suite? Is there some new coverage that the new test case can contribute compared to what we already have? And if yes, we have amplified tests and we want to give them back to the developer. Now, what is our idea of actually solving this interaction between developer and test amplification tool? We propose to put a tool in the middle that we call a test exploration tool that facilitates this interaction. This should be something like an IDE plugin where the developer is already working all the time. And there, from their code base, they can say, hey, please give me some new test cases. Our tool takes care of calling the amplification, and then it also presents the new test cases back to the developer. We show the code of the test, what is executed by it, what is this improvement that this test case is bringing to your test suite. And from there, they can directly integrate it into their maintained test suite. And this is also really the goal of us, is that we generate those test cases that they then take over into their test suite, commit to version control, and then also keep maintaining in the future as their software evolves. We implemented a prototype for this based on the dspot tool that does amplification in Java, and we also made an IntelliJ plugin that's called TestCube. And then what we asked ourselves is, what are the important factors to make this communication work well? And I conducted semi-structured interviews with 16 developers. We let them try out the tool on an example project, and then we discussed with them, what did you like here, what did you not like, how can we make this work better for you and your workflow? From analyzing these interviews, we learned a lot about how the test code should look and what kind of behavior is relevant to the developers to test, what they think about the exploration tool and how we should design this interaction, what is the information that the developers seek to judge. Is this test case valuable for me? Do I want to keep this test case in my regression test suite? And also, what is the value that these kinds of tools and processes can bring to the developer? I have two main messages that you can take away from our work here. If you have this use case of you really want a developer to take over the test case into their test suite that they will keep maintaining, it's very important that the tests are understandable to them and they test some behavior that is relevant to the developers. And that it can be more important than just improving some coverage on the numerical scale. And well, I said understandable and relevant, we also need to communicate this to the developer and be clear, make sure that they understand what is the behavior of the test that we propose and what is the impact of the test that we propose. And I think there we can really invest more in how do we tell the developers how great the tests are that we are actually producing for them. This is what we have. You can find the whole paper under the QR code. Thank you.
From the audience, I'm here.
Can you elaborate? So you said that you want to use something that is more meaningful, that some numerical values in terms of code coverage. So what kind of information you used? I don't think this.
What we saw works is if you actually show the developer the lines of code that are additionally executed by the test case. If you say you kind of make a diff of like what is the code that you have already executed, and then what is the new lines that are only tested by this test case, and you actually show these lines to the developer because they know their code, and then they see, ah yeah, in this method, this condition, this is what is happening there. And then they construct in their mind what is the scenario that we are actually testing. I would like to describe the scenario in a clearer way, but we don't really know how to do it, and for now, showing them the test work, showing them the code under test works relatively okay.
Let's thank the speaker again. And the next paper is an observational study on the development of test cases, and the presenter is Christoph Treude.
All right, thanks for the introduction. So this is work led by Mauricio Anishi, who couldn't be here, unfortunately, and just like the last paper, also with Andy Seidman. So I don't think I need to explain, given all the fantastic talks we've had in the session so far, I don't think I need to explain the importance of testing or that testing is difficult. Testing very much is still a human process, right? For many reasons, such as the Oracle problem that we heard about, there's often humans writing the test code. And we also see the software, the quality of the software out there and the quality of the testing out there that might suggest that maybe there's things we should improve. So as a first step towards that, we conducted an empirical study aimed at doing exactly what it says on the slide there, trying to understand the thought process that developers go through when they write test cases. When you give them production code, what do they actually do? How do they actually think about writing test cases? Why does the test code end up looking the way it does? So to answer this question, we did a qualitative study with 13 developers. We gave them production code from a big open source library and asked them to write test code for this and to think aloud while they were doing this. So to explain to us basically everything they do. Why are they writing this test case? Why are they putting these numbers in? Why this text? And so on. Did a lot of very thorough qualitative analysis. You can read the details in the paper about this. Iterative process, multiple authors involved, and so on. And then we validated the findings with an additional survey where we had responses from 72 developers that kind of confirmed the generalizability of our findings. Because this is a short talk, I can't go into all the details of this, but I did want to briefly talk about the framework that basically came out of our analysis. So unsurprisingly, at the center of all of this, we have the test case. What's a test case? You all know this already, of course. Describes a set of inputs, list of expectations, provides the inputs to the program on the test, compares the output against the expected behavior. So then the question we had for this work is, where does this test case come from? How do developers make up this test case? And we're basically looking at 3 different sources. Some developers heavily rely on the documentation for them to get inspiration about test cases, right? They read the documentation, see what this method is supposed to do, and then write a test case that tries to make sure that it actually does that. Others primarily look at the source code. You see an if statement, okay, maybe I can write a test case that goes this way down the if, maybe I can write another test case that goes down the other side. And another important point is the mental model. So as developers go write test cases, they develop their own mental model of what all of this looks like, what kind of behavior likely needs to be tested. Where does this mental model come from? Well, of course, it comes from the documentation and the source code. So at this point, I'd like to show you this colorful picture here. Took Mauricio quite some time to get all the colors right. Basically, we identified 3 different strategies that developers used, and it sort of depended on different people as well. Some heavily relied on the documentation, some heavily relied on the source code, and some went ad hoc. So the different colors basically show you the timeline there. Some, start with the documentation, keep coming back to the documentation, update test code, keep coming back to the documentation, and so on. Others did the same thing, but with source code instead of documentation. And yet others were all over the place, going back and forth between documentation, code, their own test cases, and so on. That wasn't our complete framework yet. There's a couple other things in here. So the test case, that one first. There is, of course, interaction between the test case and the mental model, right? Mental models, by definition, are often wrong. They keep evolving. So whenever the test case fails and the developer is very surprised by the fact that it fails, they might have to update their mental model. So the error actually should go in both directions there. They have to update their mental model, might have to go back to the test code, update the test code as well. So test cases, of course, are automated in the form of test code and hopefully satisfy some sort of adequacy criterion. So I think the thing that I did want to highlight towards the end of the presentation here are some of the recommendations that came out of this work. There's more in the paper. I don't have time to go through all of them. But what we did observe, and you've all seen this before as well, I'm sure, is a lot of copy-paste behavior. And I don't think we have really good tool support for this yet. So just by default, when you write test cases, often you do a lot of copy and paste and change a little bit here, change a little bit there. But when you do copy-paste, you make mistakes. We don't really have really good tool support that helps with templates and that helps with sort of this copy-paste behavior. Another thing that's actually related to Soneya's talk to some extent is related to code coverage. And we can replace this with specific versions of code coverage. But I feel like even as a research community, we tend to use code coverage as something that, maybe we run once a day or something to see what's going on there at the moment. What we don't really have is tool support that shows us in real time what's covered now, what else should be covered, and so on. So as we're writing, giving us suggestions that, well, maybe you should cover this branch as well. Maybe you should, this line isn't exercised at the moment. This line has a gap at the moment, and so on, and going through that. So I think that's also an interesting direction. The last one that I'd like to highlight is, so we asked participants to write test code for a particular production code method. They didn't know when they were finished. And I think many developers don't really know when testing is finished. So I think that's an interesting research area and a challenge for practitioners as well. When do you know that you're done with testing, right? When have you reached adequacy? So I think, having clear criteria for this, doing more research on this, I think would be interesting challenges for future work as well. So that's the paper, it's in TSE, download PDF link, but you also see generate citation, very important. Click on that, copy it into your overleaf, and then keep submitting. Thanks.
Thanks for the great talk. How did you measure when people were using their mental model?
So we got them to think aloud, right? So they were talking about what they were doing. And Mauricio did an excellent job at, prompting them, giving them questions that they should be responding to while they were doing this. What are you doing now? Why are you doing this? Why are you putting this exact thing there? And so on. And we did screen recording as well, so we could see what they were looking at. If they weren't looking at the production code or at the documentation, chances are they were thinking about their mental model.
Hi, thanks for the talk. Did you notice in your observation some cases in which building the mental model can be harder or less hard according to the structure of the code? So is there any testability issue that comes from the code?
I'm sure there is, because it's an empirical study that's sort of necessarily limited. All the production code we had was relatively similar to each other, so we did left pad and right pad and a few things like that. There's probably future work in exploring different kinds of production code for some definition of what these different kinds are and seeing how that affects it. So I'm pretty sure there is something there. I don't think we really have it in this paper yet.
So just because you mentioned future work, are your data available?
I don't think we have the videos anymore, unfortunately, no. Yeah, exactly.
Okay, thank you.
I'm just wondering, how do you describe the mental model? Which kind of information are you looking for when you perform this kind of experiment?
So I guess I'll give a similar answer to the previous question on a similar topic there as well. Basically, I think we defined mental model as everything where they didn't have to go back to the documentation, didn't have to go back to the source code, but basically during the think aloud said things like, my understanding is that, this method is supposed to do this and it takes this as input, therefore I should probably do that next. So it's sort of their current understanding of what's going on. No, I don't think we looked at different mental models for this.
There's a lot of questions, but we have time only for another one, and we have to take the remaining ones offline.
Okay, so I realized in your results that the documentation time was the least amount of time that the developers spent. So I wondered if it's because there's less information in the documentation, or the developers are basically, because I'm a developer, lazy to look at the documentations. Do you investigate that?
We didn't systematically investigate it. I think in this case it might be a function of just the particular production code we used. So the code, because it was an empirical study, the tasks were relatively manageable in terms of size. So I think the production code snippets we used were between 20 and 25 lines of code. There are probably systems out there where there's a lot more documentation compared to production code.
Okay, so with this session is over, and I would ask you to join me, congratulate all the speakers.